Good morning, students. Today we are going to start a new chapter, Matter and Magnetism. In chapter 4, we were discussing about moving charges and magnetism, which means how current can produce magnetic field in a conductor and its effect. In this chapter, we are mainly going to deal with natural magnets, its properties, what are the different types of magnets which exist in our nature, and how you can create an artificial magnet. Now, when you are creating an artificial magnet for certain application, you have to consider certain things. So, in this chapter, we will be studying which all things you have to consider when you are creating or when you are making an artificial magnet for an application. Magnets. If you are asked a question, what is a magnet? What will you say? You will say it is a piece of material which has both attractive as well as directive property. A magnet is a metal or a material which shows both attractive. It attracts materials like cobalt, nickel, etc. And also, when a freely suspended magnet, if you are suspending a magnet freely and if you are rotating the magnet, definitely at the end it will align in the geographical north-south direction, which means a piece of material which has both attractive as well as directive property is what we call a magnet. And the property of attraction is what we call magnetism. Now, the word magnet is coined from an island in Greece known as Magnesia, where the first natural occurring magnet was discovered by the shepherds. Okay. Next, let us see what are the basic properties of a magnet. You all know what are the basic properties. First one, it has attractive property, which means they attract pieces of iron, nickel, cobalt, etc. The second property of the magnet is directive property. As I have told you, when you are suspending a magnet freely, it always aligns in the geographic north-south direction. So, magnets are also used to find out the geographic north and south pole. Next one, like poles. Which are the like poles in a magnet? North, north and south, south. North pole and south pole, south pole. Like poles repel, whereas unlike poles attract. And this is the fundamental law which you have to consider for the magnetic poles. Like poles repel, whereas unlike poles attract. This is a fundamental law of magnetic poles. And also, imagine you have a bar magnet. You must have seen a bar magnet. If you take a bar magnet, you divide the bar magnet into, you break the bar magnet into smaller pieces. Smaller pieces means of millimeter range. You break the magnet, but each that small piece will contain a north pole and a south pole, which means monopoles will never exist. Monopoles, which means single poles, either north pole or south pole. Monopoles will never exist. In magnets, magnetic poles always exist in pairs. Divide whatever you do. If you have the tiniest magnet in your hand of nanometer range, definitely it will be having a north pole and a south pole. Next, we are going to see the terms in connection with the bar magnet. Imagine you have a bar magnet. This is a bar magnet. We are going to study certain terms in related with bar magnet, and first one is the magnetic poles. Magnetic pole means north pole and the south pole. Now, it is the region where maximum strength or maximum field of the magnet can be found. Magnetic poles, the regions of apparently concentrated magnetic strength in a magnet where the magnetic attraction is maximum is what we call the magnetic pole. And one thing which you have to take in mind is, if you have a bar magnet, the poles are situated slightly inside the bar magnet, not at the ends of the bar magnet. This is the exact end of a bar magnet, but poles will be located slightly inside the magnet. Next one is the magnetic axis. It is the line passing through the poles of the magnet. This is the magnetic axis. The line which is passing through the poles of the magnet is what we call the magnetic axis. Next one, magnetic equator. The line which is perpendicular to the magnetic axis and passing through the center of the magnet is what we call the magnetic equator. The line passing through the center of the magnetic axis and at right angles, the line which is passing through the center of the magnet and at right angles to the magnetic axis is what we call the magnetic equator. The next term which we are going to study is the magnetic length. We have two lengths in case of magnet. One is the magnetic length and second one is the geometric length. Now, magnetic length means it is the distance between the north pole and the south pole of a magnet. Magnetic length is the distance between the poles of a magnet, whereas geometric length is the length between the end points of the magnet. This much is the geometric length. So, if you look in this diagram, it is definitely clear that magnetic length is slightly less than the geometric length. Magnetic length means the distance between the poles of the magnet, whereas geometric length means distance between the end points of the magnet, and always magnetic length for a bar magnet is always less than the geometric length. Now, artificial magnets. You know, in the beginning I told you, we can make magnets using materials either by placing certain materials in the magnetic field or by passing current through them. So, these are examples for these are artificial magnets. The type pieces of iron and other magnetic materials can be made to acquire the properties of natural magnets. Such magnets are called artificial magnets. Now, the advantages of artificial magnets are, in the last chapter we studied, imagine you have a current carrying conductor, you pass the current through the conductor, then you will produce a magnetic field or it acts as a magnet, which means by varying the current or by varying the number of turns, you can increase or decrease the strength of your magnet. That is one of the advantage. Means they can be made magnetically stronger than naturally magnet, stronger or weaker depending upon the application than a natural magnet. Second one, they can be made of any shape and size. We can make artificial magnets of any shape and size according to our convenience. And the third point is the polarity, that is north pole, south pole. The polarity can be reversed whenever desired. That is, you change the direction of current, definitely the polarity of your magnet will also change. So, these are the three advantages compared to a natural magnet for an artificial magnet. First one is you can make a magnet stronger or weaker depending upon your application. Second one, it can be made of any shape and size. And the third point is its polarity can be reversed whenever desired. Next one, you take a magnet, it has a north pole and a south pole. There is a region around a magnet where the force of the magnet can be experienced, and this region is what we call the magnetic field. The region around the magnet where its force can be experienced is what we call the magnetic field. Next point, magnetic field intensity. The magnetic field intensity at any point in a magnetic field is defined as the force experienced by a unit north pole placed at that point. In the case of electrostatics, we know to find the electric field intensity, we keep a positive unit, positive charge. Same way in the case of magnetism, to find the field effect, we use a unit north pole of magnitude 1 ampere meter. So, magnetic field intensity means it is the force experienced by a unit north pole which is placed in the magnetic field, and it has a direction. It is a vector quantity. So, it has a direction, and its direction is from direction is same in which a unit north pole will tend to move if it is free to do so. Why? Because we know direction of magnetic field is from north to south. If I keep a north pole here, definitely if the north pole is free to move, then definitely it will get attracted towards the south direction. That is why we are saying it is a vector quantity whose direction is same as the direction in which a unit north pole will tend to move if it is free to do so. Next one is magnetic lines of force. Magnetic lines of force means the lines, the curved lines which represents the magnetic field. Magnetic lines of force may be defined as the curved lines used to represent the magnetic field. It is defined, or it can be also defined as the path along which a unit north pole would move if it is free to do so. And the magnetic field lines has its properties. The first property is it is closed curve which starts from the north pole of the magnet and ends in the south pole outside the magnet, and inside they return to the north pole through the interior. So outside the field lines are from north pole to south pole, whereas inside the magnet the field lines are from south to north, which means they form a closed curve. Second point, the lines will never cross each other. So imagine this is our magnet, this is a field line. No two field lines will cross each other. Why? If they are crossing each other like this, and if you keep a magnetic compass, then definitely the compass should show two directions, which is not possible in the case of magnetism, which means no two field lines will ever cross each other. Next point, they start from one end of the surface of the magnet normally. Like this is my magnet, then the field lines are starting normally to the magnet. So they start from the magnet normally. The relative closeness of lines of force is a measure of strength of the magnetic field, which means there is a magnet. You know that the field lines are closer near the poles of the magnet, which means near the poles of the magnet the field lines are closer, and this closeness represents that the field is stronger. So the relative closeness of the field lines is a measure of strength of the magnetic field, and which is maximum at the poles. And one thing which you have to take in mind regarding the last property is the lines of force have a tendency to contract lengthwise and expand sidewise. If you look in this figure, you can see they are contracting at the lengthwise portion and they are expanding at the sides of the magnet. Why? Because you know no two field lines will cross each other, and magnetic field have the property of longitudinal strain. So they contract lengthwise whereas they expand sidewise so that they won't intersect each other. Next, we are going to study Coulomb's law of magnetic force. Imagine you have two poles of a magnet having pole strength Qm1 and Qm2, called as pole strength. It can be a north pole or a south pole. And R is the distance between the poles. Then, according to Coulomb's law, the force of attraction or repulsion between the poles is directly proportional to the product of pole strength and inversely proportional to the square of distance between them. So, according to Coulomb's law of magnetism, the force of attraction or repulsion between the poles is directly proportional to the product of their pole strength and inversely proportional to the square of distance between them. Now, pole strength means it is the force with which a pole of the magnet attracts or repels the pole of another magnet. So our expression can be written as F proportional to Qm1 Qm2 divided by R square, or to change the proportionality sign we introduce a constant, so we can write F is equal to mu 0 by 4 pi Qm1 Qm2 divided by R square. This is Coulomb's law in magnetism. If I am taking Qm1 is equal to Qm2 is equal to 1 ampere meter, where ampere meter is a unit of pole strength, and R is equal to 1 meter, then what happens? F becomes equal to mu 0 by 4 pi, its value is 10 raised to minus 7 Newton. So, we can define unit pole strength as the force with which a pole of a magnet having unit magnitude, when placed in vacuum, attracts or repels another pole placed 1 meter apart from it. Unit pole strength is defined as the force with which a pole of a magnet attracts or repels another pole when placed 1 meter apart in vacuum with a force of 10 raised to minus 7 Newton. Thank you.